Morpheus from The Matrix once said, "The Matrix is everywhere. It's all around us, even now in this very room." There is a degree of truth in his statement, yet the Matrix we'll actually find is neither a pour of perplexing Japanese codes nor cool computer simulation like the movie shows us. Instead, it's a much more basic and nerdy set of lines, but certainly not less interesting and useful. Let's say you suddenly, out of your own goodwill, want to help your mum compare the prices of chicken nuggets, sausages, and beef jerky sold in 4 nearby grocery stores. You can rearrange the price data into a rectangular array and sandwich it with a pair of square brackets. This is what we call a matrix, or matrices in plural. The data in the array are called entries or elements, and they can appear as number, function, or equation. Let's call this price list matrix as Matrix M for Mum. Here we can see that its elements are presented by rows and columns. Matrix M consists of 3 rows, R1, R2, and R3, and 4 columns, C1, C2, C3, and C4. We can identify the position of an element based on these. For example, element 6 in matrix M is on the first row, R1, and second column, C2, simply stated as M12 equals 6. Hence, we can easily distinguish the elements with the same value but in different positions, such as 3.3 in the matrix, M21 and M23. Additionally, the number of rows and columns specifies the order of a matrix, expressed as M by N. Matrix M is said to be of order 3 by 4, since it has 3 rows and 4 columns. Is it possible for a matrix to only have 1 row or 1 column? Yes, it's absolutely possible. Matrix with only 1 row is called a row matrix, whereas a column matrix has a single column. A matrix can be equal with another matrix as long as they have the same order and the corresponding elements are equal. Look at the following matrix N. Is it equal to matrix M? First, check their orders. Both are 3 by 4 matrices, so the first requirement is fulfilled. Second, look at the corresponding element of the matrices. Element M11 should be equal to N11, M12 should have the same value as N12, and so on. In matrix N, some of its elements look different. But if we solve the operations first, we can clearly see that they have equal values. Hence, matrix M and N are equal matrices. We can find the unknown variable of an element based on the matrix equality. If the following matrices C and D are equal, we can obtain the value of A and B in the matrix C by putting them as linear equations. So, A plus 3 in matrix C equals 5 in matrix D, or A plus 3 equals 5, and likewise B minus 2 equals 6. In a matter of seconds, we can tell that the value of A is 2 and B is 8. Matrix is used in various disciplines, such as physics, engineering, economics, and statistics. It has an important role in construction and data encryption as well. Additionally, the digital image processing relies on convolution, which basically uses matrices and products of matrices. The signal in a seismic measurement is also modded in a matrix, where the frequencies become its elements. Now, you've learned about the basics of the matrix. To check your understanding about our discussion so far, can you identify the value of A, B, and C in the following equal matrices E and F? Share your comments below. Are you ready to take your knowledge of matrices to the next level? In our previous video, we touched on the importance of matrices and their diverse applications in fields like seismology. But did you know that there are various types of matrices beyond just row and column matrices? Now, we're going to dive deeper and explore some other fascinating matrices that will expand your understanding of this powerful tool. Rectangular and square matrices. Rectangular and square matrices are categorized by their dimension. They're defined as having an equal number of rows and columns, forming a square shape. An array of 2 by 2 and 4 by 4 matrices, for example, are the square matrices. In contrast, rectangular matrices have different numbers of rows and columns, such as the 3 by 4 and 5 by 2 matrices. Row and column matrices are included in this latter category. Triangular matrix. Triangular matrix is a subtype of square matrix, where elements above or below main diagonal are 0. Let's consider 2 3 by 3 matrices, X and Y. Matrix X is called the upper triangular matrix because it has zeros below the main diagonal, while the upper non-zero elements along with the main diagonal forms a right triangle. Inversely, matrix Y has zeros above the main diagonal, creating a triangle shape at the bottom. Hence, Y is a lower triangular matrix. We can have a triangular matrix from any order of the square matrices and may have 0 elements within the triangular-shaped elements. Diagonal matrix. Diagonal matrix is a matrix where all non-diagonal elements are 0. Matrices A and B in our examples here are diagonal matrices. Matrix C is also included in this type since the non-diagonal elements are 0, although one of its diagonal elements is 0. Identity matrix. An identity matrix, denoted as I, is a diagonal matrix where the elements of its main diagonal are all 1 while the rest are 0. If we multiply any matrix by the identity matrix, the original matrix remains unchanged. Note here that a matrix is considered an identity matrix if it has elements of 1 only on the main diagonal. So, the similar matrix with values of 1 on the anti-diagonal is not an identity matrix. Scalar matrix. A scalar matrix is almost similar to an identity matrix in that it has the same number or variable on its main diagonal and 0 everywhere else. In fact, a scalar matrix is the product of a constant and an identity matrix. We'll delve further into matrix multiplication in the next video. Null or zero matrix. Another kind of matrix is the null or zero matrix. Can you guess what it is? Yes, as the name suggests, it is composed entirely of elements equal to 0. Easy peasy. Negative of a matrix. To obtain a negative of a matrix, we simply change the signs of all of its entries. In the following example, all the positive signs in matrix D are changed to negative, and vice versa. Transpose of matrix. If we interchange the rows and columns of a matrix, we will get its transpose, denoted by subscript T. Transposing makes the order reversed. It means when matrix E is transposed to matrix ET, we interchange its rows and columns. The order 3 by 5 is reversed to 5 by 3. So if we transpose a row matrix, we'll get a column matrix and vice versa. Symmetric and skew-symmetric matrix. A matrix is considered symmetric if it is equal to its transpose, meaning that their orders and corresponding elements are the same. Hence, the symmetricity is a property that only applies to square matrices. However, a matrix also can be skew-symmetric if its transpose is equal to its negative. For example, consider matrix F. Matrix F is different from its transpose, yet the transpose and its negative are the same, Ft equals minus F. Therefore, matrix F is skew-symmetric. A matrix can be put into a few types, like the following one. Apart from being a square matrix, do you know what category matrix M can be put into? Comment below. Thank you for your continuous support, especially our valued patrons and members who have been encouraging us to keep producing more quality content.